for more than 50 years. No human mission has carried astronauts this far from Earth. Now Artemis II changes that. 4 astronauts rise from Florida, leave low Earth orbit behind, and head back toward the Moon on a journey that brings humanity into deep space once again. This is not a landing mission. It is something quieter and in some ways more important. It is the flight that must prove humans can safely return to the long road between Earth and the Moon. If this kind of space story fascinates you, please like the video, subscribe to the channel, and come along for the journey. Artemis II begins not as a machine on a pad, but as a moment in the long arc of human spaceflight. On April 1st, 2026, NASA launches 4 astronauts on the first crewed lunar flyby mission in more than 50 years, sending human beings away from low Earth orbit and back into the wider Earth-Moon region for the first time since the Apollo era. The event is historic not because it repeats the past in the same form, but because it restores a capability that has been absent for half a century. For decades, human spaceflight remains close to Earth, centered on orbiting laboratories and transport in near-Earth space. Artemis II changes that scale. It opens the deep space part of the Artemis era by placing a crew on a path that reaches outward toward the Moon and then returns home. In NASA's current framework, Artemis is more than a single launch or a single voyage around the Moon. It is a long-term exploration campaign that links lunar missions to future human missions farther into the solar system. NASA describes the program as a return to the Moon for scientific discovery, technology development, and preparation for missions to Mars. Within that structure, Artemis II holds a distinct place. Artemis I proves that the Space Launch System rocket, the Orion spacecraft, and the associated ground systems can fly together without a crew. Artemis II becomes the first time that people enter that system and test it in the deep space environment for which it is intended. In this broad sense, the mission is both a continuation and a beginning. The historical contrast behind this mission gives it much of its weight. During Apollo, crews travel to the Moon within a compressed period of intense national effort, and those flights culminate in lunar landings. After Apollo 17 in 1972, human beings no longer travel beyond low Earth orbit. Space stations, shuttles, and international partnerships reshape human flight into something more sustained and more local to Earth. Artemis II therefore stands at a turning point between 2 eras. It does not seek to reproduce Apollo exactly. Instead, it takes the long interval after Apollo and marks the start of a new outward movement. A route once used and then left quiet is opened again to a crew. The difference between low Earth orbit and the lunar region is not only a matter of distance, it is also a matter of dependence and exposure. Close to Earth, spacecraft remain near rapid support, frequent resupply, and a planet whose magnetic environment and infrastructure still shape the mission. A flight toward the Moon moves into a more isolated domain, where communication delay grows modestly, return takes time, and the crew relies more fully on the spacecraft as a self-contained system. NASA's description of Artemis II reflects this reality by treating the mission as a test of human deep space capabilities rather than only as a long trip. The broad context of the launch therefore includes a shift in operating conditions, from near-Earth routine toward true deep space practice. The mission also sits within the logic of testing. Artemis I, the uncrewed predecessor, sends Orion beyond the Moon and back on a demonstration flight that lasts several weeks and covers about 1.4 million miles. That earlier mission shows that the basic integrated system can survive launch, operate in deep space, travel beyond lunar distance, and return through Earth's atmosphere. Yet an uncrewed test cannot answer every question that matters for human flight. A spacecraft built to carry people must be judged not only by whether it moves correctly, but by whether its environment, controls, communication, and operational rhythm remain suitable for a crew in real time. Artemis II inherits that proof of concept and adds the presence of human bodies, judgment, and workload. NASA presents Artemis II as an approximately 10-day mission around the Moon and back, a test flight rather than a landing attempt. The crew travels on a free return path, meaning a trajectory designed so that the motion of Earth and Moon helps guide the spacecraft back toward Earth without requiring a full lunar orbit insertion for the basic return geometry. In the widest view, this makes the mission both ambitious and cautious. It reaches deep into cislunar space, farther from Earth than any human crew has gone in many decades, yet it does so in a way that preserves a natural path home. The mission profile reflects the role Artemis II plays in the campaign. It is the phase of proving that human beings, riding in Orion atop the full Artemis launch system, can travel out, operate, and come back safely from the lunar environment. The crew itself adds another layer of meaning at this outer scale. NASA astronauts Reed Wiseman, Victor Glover, and Christina Koch fly, alongside Canadian Space Agency astronaut Jeremy Hansen, making Artemis II both an American mission and an international one. In that sense, the flight belongs not only to a technical program but also to a modern pattern of partnership in exploration. The mission does not carry only a symbolic crew. Their task is to travel, observe, evaluate, and help judge whether the spacecraft and mission design are ready for the later stages of the campaign. At the widest level, the launch is therefore not merely ceremonial, it is operational, international, and evaluative at once. Seen in this broad frame, Artemis II is a threshold mission. Human spaceflight often advances in steps separated by long pauses, changing institutions, and revised ambitions. Launch systems are redesigned, spacecraft are retired and replaced. Even with these interruptions, the underlying motive endures. Human beings continue trying to extend reliable presence beyond Earth. Artemis II does not complete that effort, and NASA does not present it as an endpoint. Its significance comes from carrying people into the deep space architecture and turning a tested but uncrewed system into a lived environment. For that reason, the launch can be understood in the simplest possible way. Humans head back toward the Moon, not yet to land, not yet to stay, but to cross the distance again under present-day conditions and goals. Between Earth and the Moon lies a region that often appears empty in ordinary imagination, yet in spaceflight it is one of the most consequential stretches of space near humanity. Artemis II travels through this expanse, and the mission only makes sense when the scale of that corridor is understood in calm, physical terms. The Moon is not nearby in the way clouds, mountains, or even satellites in low Earth orbit are nearby. It is Earth's natural companion, but it remains far enough away that a crew leaving Earth enters a true deep space passage long before reaching lunar distance. The Earth-Moon system forms its own broad arena of motion, shaped by gravity, sunlight, radiation, and silence. This region is often called cislunar space. In simple terms, that means the space that lies between Earth and the Moon and around their shared gravitational relationship. It is not a straight road marked by fixed walls or lanes. It is a changing gravitational landscape in which Earth remains dominant close in. The Moon becomes more influential nearer its own path, and the motion of both bodies must be taken into account together. The average distance from Earth to the Moon is about 384,000 kilometers. though the exact separation changes because the Moon follows an orbit that is slightly elliptical, rather than perfectly circular. That distance matters because it turns the journey into a sustained transit. Even at great speed by human standards, a crew does not simply rise and arrive. It travels through a long interval of space where Earth grows smaller and the Moon slowly becomes a destination rather than a bright object in the sky. Seen from the wider scale, the Earth-Moon corridor is defined first by emptiness. There is no air to carry sound, no weather in the earthly sense, and no medium that gives gentle resistance to motion. A spacecraft coasts because there is almost nothing to slow it. Yet the emptiness is not featureless. It is crossed by light from the sun, immersed in the gravitational pull of Earth and Moon, and filled with energetic particles moving through interplanetary space. The sun illuminates the region harshly and without atmospheric softening. A surface in sunlight can heat strongly, while a shaded surface can become extremely cold. The space between Earth and Moon therefore presents sharp thermal contrast, governed by exposure and shadow rather than by air temperature as is known on Earth. Radiation is part of this outer setting as well. Near Earth, the planet's magnetic environment offers partial shielding from some charged particles, though not complete protection. As a mission moves outward, that protective influence changes. In cislunar space, the spacecraft and crew are more directly exposed to the surrounding radiation environment, which includes particles from the Sun and a background of higher energy particles known as galactic cosmic rays. This is one of the reasons the Earth-Moon corridor marks a real boundary in human exploration. It is not only farther away, it is physically less sheltered. The crew travels through a domain where Earth's protection becomes weaker, and the spacecraft itself matters more as a small, enclosed place moving through a broader and less forgiving environment. Distance in this region also changes communication and perception. Radio signals still move at the speed of light, so the delay between Earth and the spacecraft remains short by the standards of the solar system, but it is no longer negligible in the way it is for low Earth orbit. The crew and mission control remain closely linked, yet the exchange now carries the feel of separation rather than immediate proximity. Earth is still near enough to govern the mission, but not so near that the journey feels local. The corridor between Earth and Moon is the first region where human spaceflight becomes clearly beyond the easy reach of rapid return. The motion through this expanse is guided less by brute force alone than by trajectory. A trajectory is the path an object follows through space under the combined influence of its speed and the gravitational pulls acting on it. For Artemis II, the broad geometry is commonly described as a free return path around the Moon. In simple terms, this means the spacecraft is sent on a route that carries it outward, lets lunar gravity bend its course, and then brings it back toward Earth without requiring the basic return to depend on entering a long stay around the Moon. The path is not free in the sense of effortless. It must be designed with care and executed with precision. Yet it is free return in the sense that the Earth-Moon system itself helps shape a natural way home once the craft is on the proper line of motion. This gives the Earth-Moon expanse a quiet structural logic. The region is not empty space crossed by a straight shot. It is a gravitational conversation between two large bodies, and the spacecraft travels within that conversation. Earth holds the departing vehicle at first, then loosens its dominance as the craft moves outward. The Moon does not simply wait as a target. Its own motion and gravity alter the passage. The crew therefore travels through a region where the shape of the journey depends on celestial mechanics, meaning the lawful motion of bodies under gravity. The apparent emptiness hides a precise architecture of motion. From the perspective of the crew, this corridor is also a gradual visual transformation. Earth does not vanish at once. It recedes, changes scale, and becomes more whole as distance grows. The Moon, by contrast, changes from a distant familiar object into a physical world with clear form, shadow, and presence. The journey across this lunar space is therefore not only a transit between endpoints, it is a passage in which the spatial relationship between Earth, Moon, and crew steadily rearranges itself. Earth is revealed as one body among others, and the gap between worlds becomes something measurable, traversable, and real. So Section 2 remains at the widest physical layer of the mission. Artemis II heads into the Earth-Moon expanse, a region defined by long distance, vacuum, radiation, shifting gravitational influence, and the quiet discipline of orbital motion. Before any launch pad, before any rocket stage, before any cabin interior, the mission belongs to this larger setting. Humans head back toward the Moon by entering the broad cislunar corridor itself, where Earth's immediate closeness falls away and deep space travel begins in earnest. At the edge of the Atlantic coast of Florida, the Artemis II mission takes shape within a landscape that is both ordinary and highly specialized. Kennedy Space Center sits on Merritt Island, a low, flat stretch of land bordered by water, marsh, and open sky. It is not a mountain fortress or an enclosed industrial basin. It is a coastal plain, exposed to salt air, shifting light, sea breeze, heat, and storms. This geography matters because the mission begins here long before the rocket rises. The place itself forms the first practical threshold between the human world of roads, buildings, and routines and the outward direction of deep space flight. At this broad regional scale, the launch environment is still Earth in a very recognizable form, yet it is Earth arranged around departure. The Florida launch coast is defined by openness. The land lies low enough that the sky feels dominant even when structures stand on it. Wetlands spread across large areas, and long causeways cut through water and grass toward the pads and assembly buildings. The Atlantic lies to the east, and this seaward orientation is not accidental. Rockets launched from this coast can climb out over the ocean, reducing risk to populated land areas if debris falls during ascent. The open ocean becomes part of the safety geography of launch. Even before a vehicle is considered, the coast explains why this region is used. Spaceflight needs room, distance, and controlled exposure, and the eastern edge of Florida provides all three. The location also benefits from Earth's rotation. Near the equator, the planet's surface moves eastward faster than it does at higher latitudes. Florida is not equatorial, yet it is far enough south that launches heading east gain a modest velocity benefit from Earth's turning motion. In spaceflight, even a modest gain matters. It reduces the performance burden on the vehicle and fits naturally with launch paths that head over the Atlantic. The coast therefore offers both practical safety and physical advantage. It is a place where geography and orbital mechanics meet in quiet agreement. Weather is one of the most persistent forces in this environment. Florida's coast is warm, humid, and changeable. Clouds build quickly. Rain can form in narrow bands or wide areas. Lightning risk is taken with unusual seriousness because a launch vehicle is a tall conductive structure rising through charged air. Strong upper-level winds can place stress on the vehicle during ascent. The coast also lives within the larger seasonal reality of tropical storms and hurricanes. For that reason, the launch environment is never only a fixed site. It is a site in negotiation with the atmosphere. The pad may be still, the rocket may be ready, the mission plan may be complete, yet the wider coast still has a vote through wind, cloud, electric charge, and sea-driven weather patterns. Salt and moisture define the material character of the place as well. Sea air is corrosive. Metals, coatings, seals, and exposed equipment all experience a harsher environment when they live near the ocean. Ground facilities on this coast are not merely built once and left alone. They require constant inspection, maintenance, and renewal because the climate works slowly but continuously on every surface. The launch coast therefore shapes not only the daily look of the area, but the entire maintenance culture that supports missions. What appears calm and still in photographs is, in material terms, an environment of steady wear. The human impression of the region is shaped by scale. Roads run long and straight across flat ground. Water channels reflect the sky. Vegetation stays low compared with the height of the major spaceflight structures. This means the built elements of the launch complex, when viewed from a distance, rise sharply out of the landscape. The vehicle assembly building, service towers, lightning protection structures, and pad hardware become visible markers across otherwise open terrain. Yet in this section, the focus remains on the coastal setting itself rather than on the machinery placed within it. The land and water give those structures their meaning. Without the emptiness around them, their scale would feel different. Without the coast, the launch site would lose the broad horizon that makes departure legible. The region also sits within a long history of American launch activity. Cape Canaveral and Kennedy Space Center have been associated with major missions for decades, including Mercury, Gemini, Apollo, the Space Shuttle, and later uncrewed and crewed launches of many kinds. This continuity matters because the launch coast is not simply a patch of useful land. It is a worked landscape, shaped by repeated use for the act of leaving Earth. Roads, tracking assets, exclusion zones, protected areas, and operating procedures have all evolved with that purpose in mind. Even so, the coast never becomes abstract. Birds move through it. Water shifts with tide and weather. Heat shimmers above paved surfaces. The ancient and the engineered remain interwoven. That interweaving is especially visible in the protected natural areas around the centre. Much of the surrounding land remains wildlife refuge, and the contrast is striking. One of the most technically advanced human activities begins amid lagoons, grasses, insects, birds, and tidal rhythms. The site does not erase nature. It occupies a carefully managed part of it. The broad launch environment therefore contains an unusual balance. It is at once strategic infrastructure, coastal ecosystem, and national historical ground. Artemis II enters space from a place where all three conditions are present at the same time. Light on this coast has its own role in the atmosphere of launch. Morning brightness spreads quickly across flat water and pale concrete. Afternoon haze can soften distant outlines. At night, the pad zones and roadways become islands of artificial illumination in a wider darkness shaped by sea air and moisture. The launch coast is not visually dramatic in the way mountains or deserts are dramatic. Its drama comes from openness, exposure, and anticipation. The horizon is simple. The terrain is almost understated. That simplicity is exactly what makes the presence of a launch site feel so distinct. The coast offers a large, calm frame in which human departure can stand out clearly. So at this third regional layer, Artemis II remains a mission grounded in place, before any countdown sequence, before any ignition, before any rising column of thrust. The flight belongs to Florida's eastern edge. Kennedy Space Center occupies a coast of low land, warm air, marsh water, salt, weather, and broad sky. It is a place selected for geometry, safety, climate management, and continuity of use. In this environment, Earth still feels fully present. The sea is near. The air is heavy. The land is flat beneath the sky. Humans head back toward the moon from here, from a coastal threshold where terrestrial geography quietly prepares the way for ascent. At the center of the launch coast, the Artemis II mission narrows from broad geography into a specific piece of infrastructure. Launch Complex 39B is not merely an empty concrete rise where a rocket happens to stand. It is a carefully built interface between vehicle and Earth, a place where the spacecraft, the rocket, the tower, the power lines, the propellant systems, the water systems, and the human teams all meet in a single working arrangement. NASA describes the pad as a heavily upgraded site prepared for Artemis launches, and that description is accurate in both engineering and atmosphere. The pad exists to support a short but exacting interval in which a vehicle must be fed, checked, protected, commanded, and then released. Before liftoff, the launch system still belongs to the ground, and Launch Complex 39B is the form that ground support takes. The pad itself is only one visible part of a larger ground system. Artemis II arrives there after an 11-hour trip from the vehicle assembly building. Carried 4 miles on Crawler Transporter 2 with the integrated SLS and Orion secured to the mobile launcher. Once at the pad, the stack is not simply parked. NASA says teams begin securing the rocket, spacecraft, and launch platform to the pad infrastructure so that power supply and communications can be established between the flight hardware and ground teams. This detail reveals the true nature of the site. The pad is not a static platform beneath a finished machine. It is a live connection point. Electrical power, command pathways, monitoring systems, and environmental support all continue to pass between ground and vehicle while the mission remains in preparation. The vehicle stands vertically in public view, but in practical terms it is still tied into a wider terrestrial nervous system. The mobile launcher is central to that relationship. It serves as the support structure that carries the integrated rocket and spacecraft to the pad, and then functions as the immediate service tower beside the vehicle. NASA's current Artemis II pad updates describe the crew access arm extending from this structure and supporting entry into the White Room, the enclosed area through which personnel can access Orion. The same updates note the connection of emergency egress baskets to the mobile launcher, underscoring that the tower is not only for fueling and checkouts, but also for crew access and crew escape during the pre-launch phase. In quiet conditions, it appears as a rigid steel companion to the rocket, but its real purpose is more active. It holds the umbilical relationship between ground and flight hardware for as long as possible, delaying separation until the last seconds when launch becomes irreversible. Around this tower and pad, protective systems address the violence of launch before it happens. One of the most striking is the ignition overpressure and sound suppression system. NASA states that the water tower feeding this system holds roughly 400,000 gallons of water, released onto the mobile launcher and into the flame trench in less than 30 seconds, with a peak flow rate of about 1.1 million gallons per minute. The practical reason is simple. A launch vehicle must be shielded as much as possible from the destructive reflected pressure and acoustic energy produced by its own engines. Water becomes a form of protection. It absorbs energy, damps sound, and helps preserve both the vehicle and pad structures during the seconds of ignition and ascent. On the same site, NASA notes that the refurbished flame trench and new flame deflector are built to withstand peak temperatures of about 2,200 degrees Fahrenheit, and that more than 96,000 bricks line the trench walls. The trench itself extends about 450 feet. These details show that the pad is not an ordinary base. It is a hardened channel for heat, force, and vibration. The vertical surroundings of the pad also tell their own story about risk. NASA states that the 3 lightning towers at the pad rise to about 600 feet, taller than the vehicle assembly building. In Florida, where electrical storms are part of the natural climate, this feature is not decorative. It reflects the reality that a launch site must defend against the atmosphere even before a rocket ever ignites. The same fact sheet notes that during refurbishment, more than 1.3 million feet of copper cable were removed and replaced with about 300,000 feet of fiber cable. A reminder that modern launch support depends as much on resilient communications and control architecture as on concrete and steel. The pad therefore presents 2 kinds of protection at once. It is built to withstand the rocket below and the weather above. In both directions, it exists to manage concentrated energy. As launch approaches, the ground systems shift from passive readiness into timed procedure. NASA's launch countdown materials show engineers powering up flight hardware, checking communication links, and preparing the cryogenic systems required to load hundreds of thousands of gallons of supercooled liquid hydrogen and liquid oxygen. The published countdown sequence includes rocket cavity inerting with gaseous nitrogen, activation of the ground launch sequencer, chill down of transfer lines and propulsion systems, slow fill and fast fill operations, and a built-in countdown hold before the final commitment to tanking and terminal count. In this phase, the pad becomes a place of controlled transformation. What stands motionless above is slowly filled with propellant, electrically awakened, environmentally conditioned, and steadily handed from engineering preparation to launch readiness. The ground systems do not merely observe this change, they create it. The human side of the pad remains present even when the rocket seems to dominate every image. NASA says the launch team arrives at consoles inside the Rocco Petrone Launch Control Center as countdown begins. While non-essential personnel later leave Launch Complex 39B during the final sequence. These facts reveal a layered geography of people. Some remain at a protected distance, commanding and verifying. Others work directly at the pad while time still permits physical access. Then the site is emptied of all but what must remain. This withdrawal is one of the defining actions of the ground system. The pad begins as a place full of technicians, connections, and direct contact. It ends, just before launch, as a place intentionally cleared, leaving machinery, remote control, and timing to carry the mission the rest of the way to release. So at this layer of the mission, Artemis II is still a terrestrial arrangement held together by engineered support. Launch Complex 39B, the mobile launcher, the flame trench, the water deluge system, the lightning towers, the communications network, the fueling lines, the crew access path, the emergency escape hardware, and the control rooms together form the last architecture of Earth beneath the vehicle. The rocket appears to wait in stillness, but the pad around it is already working continuously. It powers, protects, connects, cools, fills, monitors, and prepares. In that sense, the mission does not begin with ignition. It begins here, within the ground systems, where an immense flying machine is still part of the ground, and only gradually approaches the moment when these connections must all let go. At the moment of liftoff, Artemis II becomes most legible as a single structure. The wide program, the coastal geography, and the ground systems narrow into one vertical machine that stands complete and fueled on the pad. NASA's Space Launch System in the Block 1 crew configuration rises about 322 feet tall and weighs about 5.75 million pounds at liftoff. In this form, it is not only a rocket beneath a spacecraft. It is an integrated launch stack, with Orion at the top, the launch abort system above the crew vehicle, the stage adapters and propulsion stage below, the large core stage beneath them, and the twin solid rocket boosters flanking the full height of the central body. Seen at rest, it presents an unusual combination of stillness and stored motion. Nothing about its outward posture suggests ease. Its proportions are long, upright, and severe, built for one task only, which is to leave the ground by force great enough to overcome its own enormous weight. What makes this rising structure distinctive is not only size but concentration. A launch vehicle at this scale gathers a very large amount of chemical energy into a narrow, disciplined shape. Cryogenic propellants, solid propellant, pressure vessels, avionics, guidance systems, and the crew spacecraft are all stacked in direct vertical dependence. The vehicle must remain stable while loaded, while connected to the pad, and while exposed to gravity and weather. Yet it is built for a condition that lasts only a short time. It is not designed to stand permanently. It is designed to transform. NASA describes SLS as the heavy lift rocket that launches Orion astronauts and cargo directly toward the moon in a single launch, and that description explains the whole vehicle character of Artemis II at liftoff. The stack is a complete departure system. Every major element visible from outside is part of one immediate act, the conversion of a motionless structure into a rising trajectory. The transition from stillness begins in a carefully ordered way. Before the vehicle moves, the 4 RS-25 engines of the core stage are already at full thrust, and then the 2 solid rocket boosters ignite. NASA's launch day update states that the twin boosters provide more than 75% of the thrust needed to lift the rocket from the pad, and that the combined force at liftoff is about 8.8 million pounds. In physical terms, this means the vehicle rises only when the upward force exceeds the full downward pull of its mass under Earth's gravity. Until that threshold is crossed, the rocket remains a loaded structure pressing into the pad. Once it is crossed, the relation changes immediately. Weight no longer defines the vehicle's condition by itself. Thrust becomes dominant, and the entire stack passes from supported object to accelerating body. The launch is therefore not a jump in the everyday sense. It is a transfer of control from ground support to internal power. In these first seconds, the full vehicle behaves as a single rising column. The visible motion is often described as slow, and from a distance that impression is understandable. A structure of this mass does not appear to leap. It gathers motion with authority rather than suddenness. The pad holds it fixed until the launch commit conditions are satisfied, and then the vehicle seems to free itself almost reluctantly, rising through steam, water vapor, and exhaust while remaining visually upright and composed. This outward calm is misleading only in the sense that the underlying forces are immense. The stack is already under heavy structural load. It is carrying the stress of thrust from below, resisting aerodynamic disturbances as it begins climbing through air, and managing the dynamic interaction of guidance corrections, engine performance, and overall structural flexing. Yet to a distant observer, the first clear fact remains simple. The whole machine is moving upward, intact, and all of its visible parts still belong to one unified form. At liftoff, the relationship between rocket and pad changes almost instantly in another way as well. NASA notes that the umbilicals, which provide power, fuel, and data connections during pre-launch, disconnect and retract into protective housings as the rocket rises. This is an important detail because it marks the precise end of the ground-held state. Until that instant, the vehicle is still partly an earthbound system, fed and monitored through direct physical links. Once those links are gone, the stack is fully committed to flight. The rising vehicle is no longer being sustained by external lines. It carries its own power, guidance, pressurization, and life support path forward. The launch structure that seemed inseparable from the pad becomes suddenly separate from it. The entire machine is now a self-contained upward-moving body, leaving behind the last direct hardware connections to the surface. The full vehicle character of this moment also explains why SLS occupies a special place in NASA's lunar architecture. NASA states that Block 1 is the version used for Artemis I, Artemis II, and Artemis III, and that during launch and ascent it produces about 15% more maximum thrust than the Saturn V rocket. This comparison is historically significant, but within the present section it matters mainly because it defines the kind of object seen at liftoff. Artemis II does not leave Earth aboard a small transport or a modular assembly, requiring multiple launches to create a lunar departure stack in orbit. It rises as one tall, integrated machine, built to send Orion and its crew outward in a single launch event. That is why the earlier seconds of flight feel so complete in visual terms. The whole system is present at once, and the whole system begins moving at once. There is also a human meaning to the vehicle's upward motion even at this external level. With Orion at the top, the crew rides the highest part of the stack, above the great tanks, engines, and boosters that provide the force below. Yet at liftoff the astronauts are still contained within the single body of the launch vehicle rather than experienced as separate individuals. The stack lifts as one. The people on board are carried not by a visible cabin moving independently, but by the combined performance of the entire architecture beneath them. This is why liftoff, from the outside, remains a whole vehicle event rather than a spacecraft event. The astronauts do not yet seem to travel through space in their own right. They rise as part of a single engineered column climbing away from Florida. So this fifth layer of the mission remains fixed on the moment when mass becomes motion. Artemis II stands fueled at about 5.75 million pounds, then rises under about 8.8 million pounds of thrust, carrying Orion atop the Block 1 space launch system as the umbilicals fall away and the full structure leaves the pad. In this instant the mission becomes physically undeniable. A machine that only moments earlier belongs to the ground is no longer of the ground. It is still complete, still vertically unified, still visually one body, but it has entered ascent. Humans head back toward the moon here first as a whole launch vehicle lifting free, a single towering structure turning stored force into departure. In the first part of ascent, the Artemis II launch is defined above all by the twin solid rocket boosters. Although the full space launch system rises as one integrated vehicle, the early climb belongs mainly to these two tall side-mounted motors, each one a powerful and relatively simple machine compared with the more intricate liquid-fed systems around it. NASA describes them as shuttle-derived solid rocket boosters, and during the first 2 minutes of flight they provide more than 75% of the thrust required to drive the vehicle away from Earth. Each booster stands about 177 feet tall, and at liftoff, each produces more than 3.6 million pounds of thrust, making them the dominant source of the launch vehicle's early force. In the opening phase of flight, the boosters are not secondary helpers. They are the main engines of departure in all but name, delivering the blunt, sustained push that carries the stack through the densest part of the atmosphere and into the high-speed climb away from the Florida coast. A solid rocket booster works by burning a preloaded solid propellant grain rather than feeding liquid fuel and oxidizer through pumps and valves during flight. This gives the booster phase its own character. Once ignition occurs, the process is committed. The motor does not throttle in the flexible way a liquid engine can. It burns according to its internal design. producing a thrust profile shaped mainly by geometry and chemistry already built into the propellant. NASA's Artemis II reference material notes that each booster begins with about 3.6 million pounds of thrust for roughly 25 seconds, then gradually declines to about 2.8 million pounds as propellant is consumed. This means the early ascent begins with the strongest push and then slowly eases, though it remains extremely powerful throughout the booster burn. The force is not random or explosive in an uncontrolled sense. It is engineered persistence, a long, directed release of energy designed to lift a mass of more than 5 million pounds and keep accelerating it upward. Because the boosters dominate the first ascent, they also dominate the physical experience of the initial climb. The stack clears the tower, rolls and pitches onto its proper course, and then continues through thicker air under the stern guidance of thrust and control systems. NASA states that the boosters burn for about 126 seconds, and during that time they turn the rocket from a slowly rising column into a rapidly moving ascent vehicle. The first part of flight is therefore a period of fast transition. Altitude climbs quickly, speed rises quickly, the shoreline falls away. The rocket moves from the near-stationary world of pad structures into a condition where the atmosphere itself becomes part of the engineering problem. Air pressure, aerodynamic loading, and structural response all matter intensely during this interval, because the vehicle is still low enough to be deep in the atmosphere and already fast enough for the airflow around it to become a major force. NASA's Artemis I performance review, describing the same Block 1 ascent environment, noted that the boosters helped carry the vehicle more than 27 miles from the launch site and to about 4,000 miles per hour in just over 2 minutes before separation. The Artemis II booster phase follows that same basic ascent regime. The boosters do not only push, they help steer. NASA materials on SLS booster testing refer to thrust vector control, which is the steering of a rocket by changing the direction of its exhaust flow. In simple terms, the nozzles can pivot slightly so that the line of thrust is adjusted, allowing the vehicle to maintain the proper attitude and flight path as it climbs. This matters because a launch stack is too large and too dynamically stressed to depend on passive stability alone. Wind, small imbalances, structural bending, and the planned roll and pitch maneuvers all require active control. During the booster phase, the vehicle is therefore not merely being thrown upward by raw force, it is being guided continuously. The immense exhaust plumes that seem to suggest brute simplicity are in fact part of a finely managed steering process. Early ascent is powerful, but it is also disciplined. The rocket climbs not only because it is strong, but because its strength is being directed with constant precision. There is a particular visual and physical severity to this stage because the solid boosters remain fully external and fully legible. Their pale cylindrical bodies flank the darker central core, and their plumes define the launch in a way the core stage engines do not from a distant view. The booster flames are broad, forceful, and visibly tied to the outward violence of ascent, yet their role is temporary by design. Solid boosters are used here not because they are needed for the whole journey, but because the mission needs exceptional thrust at the beginning, when the vehicle is heaviest and when gravity and atmospheric drag together impose the greatest burden. In other words, the boosters belong to the earliest problem of the mission, which is not deep space travel itself, but the act of escaping the ground and gaining momentum fast enough to leave the densest lower environment behind. Their presence tells a simple engineering truth. The first minutes of a lunar mission are dominated by the need for force now, not efficiency later. As the burn continues, mass falls rapidly because the propellant inside the boosters is being consumed at a tremendous rate. Older NASA SLS reference material states that each booster burns approximately 5.5 tons of propellant every second, even without dwelling on exact moment-to-moment values. The implication is clear. In a little over 2 minutes, the vehicle becomes dramatically lighter while still under high thrust. That combination explains why acceleration builds through the booster phase, even as the initial thrust profile gradually tapers. The stack is shedding mass almost as quickly as it's gaining altitude and speed. This changing balance between thrust and remaining weight gives early ascent its intensifying character. The rocket is no longer merely lifting, it is increasingly surging, with the boosters converting a vast store of solid chemical energy into upward motion at extraordinary speed. Then the booster phase ends as decisively as it began. NASA's Launch Day update states that the twin solid rocket boosters separate after providing most of the rocket's power during the first 2 minutes of flight. With their propellant spent, they no longer justify the mass and drag they impose. Separation therefore becomes essential. The vehicle discards them so that empty structure is not carried farther upward. For Artemis II, NASA's reference guide notes a specific change to the booster separation system, with the separation motors rotated by 15 degrees to provide additional clearance from the core stage during the jettison event. That detail shows how exact this moment must be. The boosters have done their work, but they still remain large, fast-moving bodies attached to a crewed launch vehicle. Their removal must be positive, clean, and controlled. When they fall away, the first great act of ascent is complete. The boosters that dominate the launch vanish from the mission almost as quickly as they become visible, leaving behind only the memory of the force that carried the stack through its earliest and most demanding climb. So this sixth layer of the mission remains entirely within the booster interval. Artemis II rises under the power of 2 shuttle-derived solid rocket boosters, each about 177 feet tall, each producing more than 3.6 million pounds of thrust, each burning for a little over 2 minutes while helping steer the vehicle through the harsh opening climb. Their role is brief, forceful, and indispensable. They exist for the first burden of the mission, the burden of lifting a fully loaded deep space crew vehicle away from Earth and accelerating it through air with overwhelming strength. In these moments, humans head back toward the moon, not yet through the quiet endurance of long-duration flight, but through the fierce, short-lived labor of the boosters, whose work is to make ascent possible and then disappear. After the solid rocket boosters fall away, the ascent enters a quieter but no less important phase. The visual violence of the launch changes character. The great side-mounted motors that dominate the first 2 minutes are gone, and the vehicle continues upward under the power of the central core stage alone. NASA's launch timeline for Artemis II places booster separation at about 2 minutes and 9 seconds after liftoff, and from that moment the core stage becomes the primary source of thrust. This stage is the backbone of the Space Launch System, the long central body that has been carrying the upper stage, Orion, and the crew from the beginning, but which now stands fully revealed in its role as the main sustaining engine of ascent. It is not a brief transition piece. It is the long middle force of the climb, taking over once the opening burden of brute liftoff has passed, and carrying the mission the rest of the way through first stage flight. NASA describes the SLS core stage as 212 feet tall and 27.6 feet in diameter, the tallest stage the agency has ever built. It contains the large tanks for cryogenic liquid hydrogen and liquid oxygen, the flight computers, major avionics, and the structures that support both the rocket above and the thrust below. In simple terms, it is a fuel tank, a control system, and a structural spine combined into one immense flight stage. Its scale matters because the boosters, for all their force, are temporary assistants to a central machine that must keep working for much longer. The core stage holds approximately 537,000 gallons of liquid hydrogen and 196,000 gallons of liquid oxygen. It feeds that propellant to the 4 RS-25 engines mounted at its base, and in doing so it turns stored cryogenic mass into the sustained upward motion needed for the long climb beyond the thick lower air. Those 4 RS-25 engines give the core stage its character. NASA notes that the RS-25 is a veteran engine design with shuttle heritage, one of the most extensively tested large rocket engines ever built. For SLS Block 1, the version used for Artemis I, Artemis II, and Artemis III, 4 RS-25 engines work together in the core stage, burning liquid hydrogen and liquid oxygen. NASA states that these engines together provide about 2 million pounds of thrust for the roughly 8-minute climb to orbit. That figure explains the distinction between the booster phase and the core stage phase. The earlier part of ascent depends on overwhelming additional force from the solid boosters. This part depends on endurance, controllability, and efficiency in a liquid propellant engine system that can sustain precise thrust while the vehicle grows lighter and continues to accelerate. The core stage does not replace spectacle with weakness. It replaces spectacle with disciplined continuation. The nature of this propulsion changes the feel of flight. Liquid engines can be controlled in ways that solid motors cannot. They are part of a plumbing system in which pumps, valves, injectors, combustion chambers, and nozzles all work in continuous balance. The propellants are extremely cold, and they must be delivered steadily and reliably, while the vehicle is under load and still climbing rapidly. NASA notes that the core stage feeds about 1,500 gallons of propellant each second during ascent. That extraordinary flow rate gives a sense of what the stage is doing in these minutes. The vehicle is not simply burning fuel in an abstract way. It is emptying enormous cryogenic tanks at high speed while the engines transform that flow into controlled thrust. The climb after booster separation is therefore a period of constant internal motion inside the stage itself, even though from outside the rocket now appears cleaner, narrower, and almost calmer than it did at liftoff. This is also the part of ascent in which the core stage's structural role becomes especially clear. NASA's descriptions emphasize that the core stage supports the weight of the payload, the upper stage, and the crew vehicle while also carrying the thrust loads from its own engines and, earlier, from the boosters attached to it. After the boosters separate, the stage is no longer sharing the climb with large side structures. It becomes the sole lifting body of first stage flight, holding the vehicle together while continuing to guide it upward. The atmosphere is thinning, but the demands on the rocket remain exacting. Guidance must remain stable. Engine performance must stay within bounds. The stage must continue to bear the loads of the spacecraft above while propellant mass rapidly drains away below. In this interval, the core stage appears almost like a long narrow bridge between the crew at the top and the engine force at the bottom, a bridge that is itself disappearing second by second as its propellant is consumed. NASA's Artemis II launch update places launch abort system jettison at about 3 minutes and 13 seconds after liftoff, after the vehicle has climbed above the densest atmospheric regime. That detail helps define the core stage interval without changing its focus. By this point, the rocket has moved beyond the harshest lower air conditions of the ascent, and the central stage continues its work in a different environment from the one that exists at pad departure. The vehicle is now higher, faster, and no longer carrying certain protective hardware that was needed earlier in the climb. Yet the core stage remains the engine of progress. its 4 RS-25 engines continue to operate through the middle ascent, carrying Orion and the stages above toward the point at which first stage propulsion will finally end. The timing is notable here. NASA says core stage main engine cutoff for Artemis II occurs at about 8 minutes and 2 seconds after launch. The stage is therefore active for far longer than the boosters and is responsible for most of the sustained powered climb after the initial violent opening has been completed. Because the stage burns liquid hydrogen and liquid oxygen, its performance is tied to an engine system known for high efficiency. NASA notes that SLS takes advantage of the longer S-25 development history while adapting it for present mission needs. This matters because the core stage interval is a phase of refinement as much as force. The rocket has already proved it can leave the pad. Now it must keep doing the more exacting work of sustaining acceleration, shaping the climb, and carrying the mission cleanly to the edge of first stage completion. The core stage is designed to operate for approximately 500 seconds before separating. That number is central to its identity. The stage is neither a short impulse motor nor a long in-space cruiser. It is the measured middle instrument of ascent, built to work for just over 8 minutes and then disappear once its task is complete. Then the interval ends with great precision. NASA's live Artemis II update states that main engine cutoff completes at about 8 minutes and 2 seconds, with core stage separation following at about 8 minutes and 14 seconds. By then, the long central backbone of the launch has done all it can do. Its propellants have been spent in service of ascent. Its engines have provided the sustained force after booster separation, and its structural duty has carried the spacecraft and upper hardware upward through the first major propulsion phase of the mission. The stage does not fail or fall away suddenly in the manner of an accident. It reaches the end of its designed life in flight and releases the rest of the mission from beneath it. That is the whole meaning of this 7th layer. Artemis II continues upward through the long work of the core stage. The tall cryogenic spine of SLS, which takes over after the boosters, burns for about 8 minutes, and then ends its part of the journey at the exact threshold where first stage ascent is complete. Once the core stage shuts down and falls away, the Artemis II mission passes into a different kind of powered flight. The heavy labour of ascent has ended, and the vehicle is no longer a towering launch stack fighting through the dense lower atmosphere. What remains is Orion attached to the interim cryogenic propulsion stage, or ICPS, a much smaller upper stage designed for precise in-space propulsion rather than brute liftoff force. NASA describes the ICPS as the in-space stage used for the first 3 Artemis missions, and for Artemis II, its role differs in an important way from Artemis I. Instead of directly sending Orion to the Moon, it reshapes the spacecraft's early Earth orbit path, raising and refining that orbit while the crew remains relatively close to home. The ICPS is modest in size compared with the core stage beneath it, yet it is still a substantial flight system. NASA says it measures about 45 feet tall and about 16.7 feet in diameter. It is powered by a single RL-10 engine using liquid hydrogen and liquid oxygen, producing about 24,750 pounds of thrust. That figure is tiny compared with the millions of pounds produced during liftoff, but the comparison is misleading if taken alone. The upper stage does not exist to lift the whole mission from the pad. It exists to perform exact orbital work after the roughest part of ascent is over. Its propulsion is quieter in scale, but more surgical in purpose. In this phase, Artemis II no longer needs overwhelming thrust. It needs disciplined adjustment. NASA's daily mission plan states that after the Space Launch System main engines cut off, Orion and the ICPS separate from the rest of the rocket and continue together in Earth orbit. About 49 minutes after launch, the ICPS engine fires to raise the perigee, the lowest point of the spacecraft's orbit, to a safe altitude of 100 miles above Earth. About an hour later, when Orion reaches that low point again, the stage fires a second time to continue raising the spacecraft into a high Earth orbit. This gives the upper stage phase a very specific identity. It is not a single immediate departure burn. It is a measured two-step reshaping of near-Earth motion, turning the vehicle's first orbit into a broader, safer, more deliberate path. This is why the upper stage belongs to a different physical regime from the rocket parts below it. The boosters and core stage operate while the mission is still dominated by gravity, atmospheric drag, structural loading, and the urgent need to gain altitude and speed. The ICPS operates after reaching space, when the challenge is no longer to clear the pad or survive the thick air, but to place Orion on the correct orbital geometry. NASA's April 2nd mission release says the first ICPS burn places Orion into an elliptical orbit around Earth, and the second planned burn raises it into a high Earth orbit, extending about 46,000 miles above Earth, for roughly 24 hours of system checkouts. The stage therefore shapes distance and timing more than spectacle. Its work is orbital architecture. That distinction is reflected in the engine itself. NASA says the RL-10 flying on Artemis II is the RL-10C2, a close derivative of the engine flown on Artemis I, with an upgraded ignition system and active propellant utilization control to improve efficiency. The agency also notes that for Artemis II the stage performs the perigee and apogee raise burns, while Orion later carries out the translunar injection burn with its own main engine. That division of labour is important because it defines the upper stage interval with unusual clarity. The ICPS is not asked to do everything. It is asked to do its own carefully bounded part, using restartable cryogenic propulsion to refine Orion's Earth orbit before releasing the spacecraft to operate independently. In this mission, precision of sequence matters as much as force. The geometry created by these burns also changes the meaning of the crew's first day in space. NASA's mission agenda says the astronauts then have about 23 hours to conduct a thorough checkout of Orion systems, while still relatively close to home. The upper stage makes that possible by placing the spacecraft into the high Earth orbit that serves as the setting for those early evaluations. In that sense, the ICPS is not only a propulsion stage, it is the stage that carves out a temporary orbital neighbourhood for the crew, a region where they remain in space, remain far above Earth, yet have not fully left Earth's orbital domain. This makes the upper stage phase feel transitional in the deepest sense. The mission is already beyond launch, but it is not yet a long outbound voyage. It is being positioned. The Artemis II profile also gives the ICPS a secondary operational role after its main burns are complete. NASA states that once Orion separates from the stage, the astronauts use a target affixed to the outside of the ICPS as a visual marker for a proximity operations demonstration, effectively using the spent upper stage as a stand-in object for manual handling tests. The daily agenda says Orion practices flying toward and around it, and then the ICPS performs its own disposal burn. This means the upper stage remains useful even after its propulsion job is done. It becomes, briefly, a controlled object in nearby space, supporting the crew's evaluation of Orion's handling qualities before being deliberately removed from the mission scene. That disposal is an essential part of the stage's identity. NASA's April 2nd release says that after Orion backs away, the ICPS performs a disposal burn and re-enters Earth's atmosphere over a remote region of the Pacific Ocean. The stage is therefore temporary in the most literal sense. It rises into space attached to Orion, performs two orbit-raising burns, serves briefly as a target for proximity operations, and then is intentionally sent away to destruction. Nothing about it is built for permanence. Unlike Orion, it is not a reusable habitat or a returning spacecraft. It is a purpose-built transitional engine room, present only long enough to shape the crew's first orbital condition and then vanish from the mission. Its life in flight is short, but exact. So this 8th layer of the mission remains entirely within the upper stage interval. Artemis II continues after core stage separation with Orion attached to the ICPS, a 45-foot cryogenic stage driven by a single RL, 10-engine, producing about 24,750 pounds of thrust. It fires first to raise perigee, then again to lift the spacecraft into a high Earth orbit, extending about 46,000 miles above the planet, after which Orion separates and the stage is ultimately disposed of over the Pacific. In this phase, humans head back toward the Moon through restraint rather than violence. The mission is no longer being hurled upward. It is being placed, adjusted, and carefully handed forward by the small, precise upper stage that finishes its work close to Earth and then disappears. Once Orion separates from the upper stage and begins to stand on its own in space, the spacecraft becomes legible as a distinct body rather than as the topmost element of a larger launch system. At this point, what matters first is form. Orion is not shaped like an aircraft or a long station module. Its visible character is built around a compact crew capsule joined to a cylindrical service section behind it, with a blunt heat-shielded base, sloping conical sides, a protected forward end, and broad solar arrays extending outward after launch. NASA describes Orion as the spacecraft that carries and sustains the crew on Artemis missions to the Moon and returns them safely to Earth. And from the outside, that purpose is visible in the geometry alone. The shape is not decorative. It is the outer consequence of launch, deep space transit, and high-speed return being combined into one spacecraft. The most recognizable part of Orion is the crew module, the conical capsule that forms the forward body of the spacecraft. NASA's current spacecraft component summary gives the crew module a height of about 11 feet and a diameter of 16.5 feet. Those proportions make it compact by the standards of modern space habitats, yet broad enough to serve as a real deep space cabin rather than a very narrow ascent capsule. From the outside, the crew module appears as a controlled compromise between aerodynamic and thermal demands. Its sloped side walls narrow upward toward the docking end, while the wide circular base provides the large surface needed for atmospheric return. The vehicle is therefore shaped not only for life in vacuum, but for eventual passage back through Earth's atmosphere at far higher speeds than ordinary low-orbit return vehicles must endure. Along the outside of this capsule, NASA identifies two major protective surfaces, the backshell and the heat shield. The backshell covers the cone-shaped sides of the crew module and is made up of about 1,300 thermal protection tiles. NASA says these tiles are based on silica fiber materials similar to those used on the Space Shuttle, and are intended to protect Orion from both the cold of space and the intense heating of re-entry. This gives the outer skin a dual role. It is not simply armor against return heating. It also serves as the spacecraft's protective shell during the long cold intervals of deep space. The backshell therefore makes the capsule appear smoother and more continuous than its internal structure would suggest. Beneath that outer tiled layer lies the pressure vessel, but from outside the visible message is simpler. Orion carries a carefully engineered thermal skin because the same body must endure vacuum, sunlight, shadow, and then the violence of atmospheric return. At the bottom of the capsule sits the feature that most clearly explains Orion's role as a lunar return spacecraft. NASA describes the crew module base as being covered by the world's largest ablative heat shield, measuring 16.5 feet in diameter. The outer surface uses avcoat, a reformulated version of the material used on Apollo capsules. During entry, this material ablates, meaning it gradually burns away in a controlled manner to carry heat off the spacecraft rather than allowing that heat to pass inward. NASA says Orion's heat shield is built to protect the spacecraft during return at about 25,000 miles per hour and at temperatures approaching 5,000 degrees Fahrenheit. This makes the base of Orion more than a structural bottom. It is the defining face of survival for the return home. When viewed from outside, the spacecraft's wide circular underside quietly announces that Orion is built not only to leave Earth, but to come back from the Moon at extreme speed and remain habitable through that descent. At the opposite end of the crew module, the outer form narrows toward the forward bay cover and docking area. NASA explains that the forward bay cover protects the top portion of the capsule and Orion's parachutes during launch, orbital flight, and re-entry, and that it is tiled with the same thermal protection system used on the back shell. Beneath this area lies Orion's tunnel and docking hatch, which NASA notes are designed to allow astronauts to move between the crew module and other spacecraft. This means the pointed upper end of Orion is not merely a capped nose. It is a working interface, a protected region that must serve both as a sealed exterior surface and as the place where future docked operations can occur. Even the windows in this area reflect that mixed purpose. NASA's Orion window description says the hatch window uses 3 panes in a hybrid glass and plastic design, with different panes handling vacuum protection, heat resistance, and redundancy. From outside, the forward end therefore combines shielding, visibility, and connection in one tightly packed surface. Once Orion is above the atmosphere, the spacecraft's silhouette changes further as the coverings around the service module are discarded. NASA says the European service module sits within a housing about 17 feet in diameter during launch and is surrounded by 3 spacecraft adapter jettison fairing panels that protect it from heat, wind, and acoustic stress during ascent. After that phase, the fairings are jettisoned and the solar arrays unfold to span about 62 feet. This creates one of the most striking features of Orion's exterior in flight. What begins as a compact launch shape becomes a much wider deep space form, with 4 array wings extending outward from the service module. The spacecraft no longer appears as a sealed launch capsule alone. It becomes a balanced orbital object with a central body and long symmetrical extensions, visibly adapted to the quieter environment of space rather than the compressed demands of ascent through air. The service module itself changes the look of Orion even before one considers what it does. NASA describes it as a cylindrical, unpressurized module about 13 feet high, attached behind the crew module. From the outside, it gives Orion a 2-part identity. The front half is conical and heat-shielded, unmistakably a return capsule. The aft half is cylindrical and more open in visual structure, a deep space companion body surrounded by engines, tanks, and the roots of the solar arrays. Yet in this section, the importance lies in appearance rather than in function. The service module makes Orion look less like a simple capsule and more like a spacecraft built for sustained travel. It lengthens the body, gives the vehicle a visible aft section, and turns the crew module from a standalone re-entry shape into the forward element of a larger lunar spacecraft. Even small exterior details reinforce this identity. NASA notes that the crew module includes 12 reaction control system thrusters, used after separation from the service module during return, while other NASA Orion materials describe windows and docking camera views as part of how the crew monitors nearby objects and spacecraft operations. These openings, ports, and control surfaces do not dominate Orion's appearance from afar, yet they prevent it from seeming like a sealed shell without agency. The exterior is studded with purposeful features, each one small relative to the whole body, yet each contributing to the sense that Orion is a working machine rather than a passive capsule. The outer surfaces therefore carry a quiet complexity. They remain clean and restrained in line, but they are built for orientation, observation, docking, stability, parachute deployment, and the severe thermal transitions of a mission beyond low Earth orbit. So this ninth layer of the mission remains with Orion's exterior alone. The spacecraft presents itself as a compact conical crew module about 11 feet high and 16.5 feet across, shielded by a tiled back shell and a 16.5-foot ablative heat shield, narrowed toward a protected forward docking end, then extended aft into a cylindrical service module with solar arrays that unfold to span about 62 feet. Nothing about this form is accidental. Every outer line reflects the demands of ascent, vacuum, return, and human travel beyond low Earth orbit. In this visible shell, humans head back toward the moon inside a spacecraft whose exterior already tells the whole quiet story of what it must survive. Behind Orion's conical crew capsule sits the part of the spacecraft that makes long flight possible. NASA calls it the European Service Module, and the description is exact in both engineering and meaning. It is the spacecraft's supporting body, attached below the crew module and carrying the systems that let Orion travel, maneuver, stay powered, remain thermally balanced, and supply essential consumables during the mission. From the outside, it appears less protective than the crew capsule and less visually dominant than the heat shield. Yet in practical terms, it is the working lifeline of the whole spacecraft. NASA's own summaries describe it as the powerhouse of Orion, responsible for propulsion, electrical power, thermal control, and life support consumables including water, oxygen, and nitrogen. The service module is not an American-built afterthought attached to a NASA capsule. It is a major international contribution supplied by ESA and built by Airbus, with components coming from multiple European countries and the United States. NASA's Artemis II press material notes that workers across 10 European countries and the United States contribute parts for it, and that the Artemis II module is assembled in Bremen, Germany, before shipment to NASA. This gives the spacecraft a visible international character. Orion's forward body belongs to the American crewed capsule tradition, but the section behind it is a European-built systems module that carries much of the burden of survival and motion. From the outside, the union is seamless. In program terms, it is one of the clearest physical expressions of international partnership in Artemis. Power is the first of the service module's lifelines. Once Orion is in space, it no longer depends on launch umbilicals or on any support from the ground. NASA states that the European Service Module generates electrical power through 4 solar array wings, and an Artemis image release says those 4 wings together draw in about 11 kilowatts of power from the sun. That electricity supports spacecraft systems across the mission, allowing Orion to function as an independent deep space vehicle rather than a short-lived capsule riding stored battery energy alone. The outer silhouette of the arrays therefore tells an important truth. They are not decorative wings or stabilizers in the atmospheric sense. They are broad collecting surfaces that convert sunlight into the steady electrical flow needed for navigation, environmental control, communications, and spacecraft operations. The arrays make Orion visibly self-sustaining in space. Propulsion is the second lifeline, and in many ways the most consequential one. NASA says the European Service Module is responsible for Orion's main propulsion, orbital maneuvering, and position control. In the Artemis II mission agenda, NASA specifies that Orion performs its translunar injection burn using the main engine mounted on the European Service Module, and describes that engine, also called the Orbital Maneuvering System Engine, as producing up to 6,000 pounds of thrust. This means the service module is not merely a support bus riding behind the crew cabin. It is the part of Orion that changes the spacecraft's path in the most decisive ways. After launch vehicles and upper stages finish their work, the service module becomes the source of the major maneuver that sends the crew away from Earth and toward the Moon. Its propulsion role is therefore not secondary. It is the internal continuation of the launch system in spacecraft form. That propulsion function extends beyond the single large engine. NASA's component summaries say the service module is responsible for position control as well, which means it supports the smaller attitude and maneuvering actions that keep Orion correctly oriented. A spacecraft in deep space must continually manage pointing, rotation, and small corrections. It must keep the solar arrays in useful relation to sunlight, maintain communication geometry, and orient itself properly for burns and operations. Even when nothing dramatic appears to be happening, the spacecraft is held in orderly motion by these quieter control functions. The service module is therefore the source not only of major change in trajectory, but of calm ongoing discipline in how Orion points and moves through space. It is the spacecraft's mechanical steadiness made external. Thermal control is another lifeline carried by the same section. NASA repeatedly includes thermal control in its basic description of the European Service Module, and that brief phrase carries a large practical meaning. Deep space does not provide a mild background climate. Surfaces in sunlight can become very warm, while shaded structures can become extremely cold. A crewed spacecraft must keep equipment and internal systems within allowable temperature ranges despite those outside extremes. The service module therefore helps manage heat as something that must be moved, rejected, conserved, and balanced. In this sense, it acts like an external caretaker for the spacecraft's internal condition. The crew module may provide the protected volume for human beings, but the service module works continuously to keep that protection sustainable. Thermal control is not a dramatic event. It is a persistent act of balance that allows all other systems to function normally. The same is true of consumables. NASA states that the service module provides water, oxygen, and nitrogen for the crew. These are not optional comforts. They are the quiet material basis of a human presence inside Orion. Water supports both direct crew needs and broader spacecraft functions. Oxygen is central to breathing. Nitrogen helps create and manage a livable cabin atmosphere. By placing these supplies in the service module, Orion separates the inhabited volume from much of the stored support mass that keeps that volume viable. This arrangement gives the spacecraft a kind of anatomical logic. The crew capsule is the inhabited forward body, but the service module behind it is where much of the sustaining flow originates. It is not where the astronauts live, but it is where many of the things that make living possible are carried and managed. From the outside, all of these functions are held in a cylindrical structure that appears more utilitarian than the crew module ahead of it. NASA's spacecraft component page identifies it as an unpressurized module attached below the crew capsule. That fact matters because the service module is not meant to be a shirt-sleeve habitat. It is an exposed working section, built around tanks, engines, support equipment, and array attachments rather than crew seating and protected interior volume. Its visual complexity reflects that role. The crew module is a sealed shelter. The service module is an operating platform. Yet the two remain inseparable during the mission's deep space phases. One provides habitable space. The other provides many of the conditions that let the space remain useful across days in cislunar flight. The service module's final importance lies in its temporary nature. NASA's basic Orion descriptions note that the service module supports the spacecraft in space, while the crew module is the part that ultimately returns to Earth. The service module is therefore a lifeline body meant for the outward and return voyage through vacuum, but not for the final descent through the atmosphere. Its purpose is to sustain Orion for as long as propulsion, electrical power, thermal control, and consumables are needed in space, and then to separate before re-entry. That design gives the spacecraft a clear division of labor. The crew module is built to survive the plunge home. The service module is built to make the journey itself possible. In this 10th layer of the mission, humans head back toward the moon with their survival wrapped not only in the capsule ahead, but in the service module behind it, the external system body that powers, steers, cools, and sustains Orion all the way through deep space. Inside Orion, the journey becomes human in a more immediate sense. The crew module shell is not simply the forward piece of the spacecraft seen from outside. It is the pressurized body that creates a habitable interior, the sealed capsule in which the astronauts live and work on the way to the moon and back. NASA describes the crew module as the pressurized part of Orion and the only portion that returns to Earth at the end of the mission. That description captures its basic meaning. Everything outside it may guide, power, or protect the spacecraft, but this shell is the place where human presence is actually enclosed. It is the boundary that separates breathable interior from vacuum, organized workspace from cosmic emptiness, and survivable habitat from the uninhabitable conditions beyond the hull. The underlying structure of that shell is called the pressure vessel. NASA says the pressure vessel consists of 7 large aluminum alloy pieces joined together using friction stir welding, producing a strong, lightweight, airtight capsule. This matters because Orion's crew module is not built as a thin skin draped over an internal frame in the ordinary sense. Its pressurized body is itself a primary structural form. It must hold cabin atmosphere, endure launch and return loads, support the interior hardware, and remain reliable across mission phases that range from ascent vibration to quiet deep space flight to high-speed atmospheric entry. The 7 major structural pieces include the barrel, the tunnel, the forward and aft bulkheads, and 3 cone panels. In this construction, the shell is not an outer decoration over a more important interior. It is the first indispensable fact of the interior. Without the vessel, there is no cabin at all. This sealed vessel also defines the scale of human life inside Orion. NASA states that the crew module can accommodate 4 crew members for up to 21 days without docking to another spacecraft. That duration and crew number help explain the form of the shell. It is not a roomy station environment intended for months of movement through large interior spaces. It is a compact deep space capsule, designed so that 4 people can work, rest, eat, observe, and endure a multi-day mission within a constrained but carefully arranged volume. The shell therefore represents a balance between mass limits and habitability. It must be small enough to launch and return efficiently, yet large enough to contain 4 suited astronauts during the demanding phases of ascent and entry, and to support them during the quieter days in between. The crew module is, in effect, a limited world sized precisely for its mission. Inside this shell, NASA says an aluminum structure of crisscrossing beams called the backbone assembly provides the floor structure where the crew seats are attached and where stowage lockers are located. The backbone is a 9-piece bolted structure that provides additional structural support for the crew module. This inner framework gives the sealed volume order, A pressurized shell by itself would only provide empty enclosure. The backbone turns enclosure into a usable room by creating a floor, mounting points, and organized places for storage and restraint. Its presence shows that the cabin is not arranged like a simple open chamber. It is a compact engineered interior in which every object must have a secured place, and every crew position must be structurally integrated with the shell around it. Even the floor is part of a larger logic of survival, efficiency, and control. The seats attached to this internal structure are one of the clearest ways the shell becomes a human environment. NASA says Orion's crew module includes 4 crew seats, and that the seats are designed to accommodate nearly 99% of the human population. NASA testing at Johnson Space Center further notes that the seating design is evaluated across a very wide body size range, with adjustable seat pans, foot plates, armrests, and controller mounts, so astronauts of very different sizes can safely reach and operate the controls while wearing pressure suits. This means the shell is not shaped around an abstract average person. It is built around the practical reality that real crews differ in size, posture, reach, and movement. The seat system becomes part of the shell's human geometry, fixing bodies in place during launch and entry, while still allowing the cabin to function as a workspace once the harsher dynamic phases have passed. The hatches and windows give this shell its openings without weakening its primary duty. NASA notes that the crew module includes mechanisms that allow entry and exit through hatches, provide docking capability for on-orbit activities with other spacecraft, and support separation or jettison functions when required. Testing at Johnson Space Center evaluates crew egress through both the side hatch and the docking hatch, showing that Orion's shell is designed not only to hold pressure, but to allow controlled passage in ordinary and emergency conditions. The windows are part of the pressure vessel itself, and NASA has described Orion's hatch windows as multi-pane designs, using glass and acrylic to provide both strength and visibility. These openings therefore do not interrupt the logic of the shell. They extend it. Orion's cabin remains a sealed protective body, yet it is also a place from which the crew can see, guide operations, and when necessary, leave. Protection is built into the shell in more ways than pressure alone. NASA says the sealed capsule provides radiation protection needed to safeguard crew and spacecraft systems from cosmic and solar radiation in deep space, as well as micrometeoroid protection from the space environment. NASA also notes that, in the event of a solar radiation event such as a flare, crew members can shelter themselves using large stowage lockers on the floor of the capsule and the dense materials on board as added shielding. These facts reveal an important truth about the shell. It is not only a barrier against vacuum, it is a layered protective environment whose structure, stored materials, and compact arrangement all contribute to survival. The cabin wall is therefore never just a wall. It is part of a system of shielding, enclosure, and contingency protection shaped by the realities of deep space flight. The cockpit arrangement completes the transformation from vessel to lived interior. NASA states that a cockpit with glass displays allows full control of Orion by the crew, and that the astronauts can command the spacecraft using 3 display screens, physical switches, rotational and translational hand controllers, and cursor control devices. This means the shell is not merely where people are carried, it is where they actively govern the vehicle. The cabin's inner surfaces, seat positions, controller mounts, windows, and structured floor are all arranged around this operational fact. Orion's crew module is a protective shell, but it is also a command room compressed into capsule form, where survival, observation, and spacecraft control occupy the same limited volume. The interior therefore remains small, but it is not passive. It is an active human workspace contained within a strongly built and carefully shaped envelope. So this 11th layer of the mission remains entirely within the crew module shell. Orion's pressure vessel is built from 7 welded aluminum alloy pieces, strengthened internally by the backbone assembly, fitted with 4 adjustable seats, open through hatches and windows, and organized as a sealed command and habitation volume for 4 astronauts on a mission lasting up to 21 days. It protects against vacuum, radiation, and small impacts while giving the crew a controlled interior from which to live and work. In this shell, humans heading back toward the moon are no longer only passengers of rockets and stages. They are enclosed inhabitants of a small, deliberate world, carried inside a structure whose first duty is simply to keep that world intact. Inside Orion's crew module, survival depends on a continuous set of quiet processes that rarely present themselves as dramatic events. NASA groups these functions under environmental control and life support systems, often shortened to ECLSS, and describes them as the systems that make the capsule a habitable and safe place for astronauts on deep space missions. In practical terms, this means the spacecraft must do for the crew what Earth does automatically for life on the ground. It must maintain pressure, keep air breathable, remove unwanted gases and moisture, provide water, manage waste, and hold the interior within a temperature range that people and electronics can tolerate. These tasks are not separate conveniences added after the vehicle is built. They are part of the basic condition that allows Orion to function as a human spacecraft at all. NASA says that inside the crew module these systems maintain cabin temperature, pressure, humidity, oxygen, and carbon dioxide levels, keeping the crew healthy and comfortable on long missions. That brief description reveals the life support loop as a balancing act rather than a single machine. Pressure must remain high enough and stable enough for normal breathing. Oxygen must be present in the proper amount. Carbon dioxide, continuously exhaled by the crew, must be removed before it accumulates to unhealthy levels. Humidity must also be controlled, because people release water vapor through breath and perspiration, and that moisture can condense in unwanted places or degrade comfort and equipment performance. The spacecraft therefore treats the cabin not as a sealed room that can simply be closed and forgotten, but as an active internal environment that must be constantly adjusted while 4 people live inside it. NASA's crew systems reference states that atmosphere revitalization is the highest priority on deep space missions. The phrase is technical, but the idea is simple. The air has to be renewed continuously, even though Orion is not an open system taking in fresh outside air. NASA says Orion's life support must not only provide oxygen and remove carbon dioxide, but also prevent gases such as ammonia and acetone, emitted in small amounts by humans, from building up inside the cabin. It must also provide adequate ventilation and filter particles and microbes. In other words, the spacecraft must keep the air moving, keep the air clean, and keep the invisible byproducts of human metabolism from slowly turning the cabin into an unsafe place. What appears to the crew as ordinary breathing is supported by a hidden rhythm of circulation, sensing, removal, and replacement. For this reason, NASA emphasizes that Orion uses a regenerable carbon dioxide and humidity removal system. Regenerable means the system can be used again, rather than relying entirely on single-use cartridges that are discarded once filled. NASA describes this as important for saving mass and volume on deep space vehicles, and the reasoning is straightforward. On a mission beyond low Earth orbit, every kilogram matters, and resupply is not available. A life support system must therefore be dependable but also efficient in how much replacement material it requires. Orion's air system is built to remove carbon dioxide and humidity, while conserving spacecraft mass and cabin volume, which means that even the invisible chemistry of the atmosphere is shaped by the broader engineering economy of the mission. Life support is not only about keeping the crew alive, it is about doing so in a spacecraft small enough and light enough to travel to the Moon and back. Temperature control forms another part of the same loop. NASA states that Orion's environmental systems continuously monitor temperature, humidity, and pressure so they can detect and respond to unsafe conditions, and that the environmental control system removes excess heat, humidity, and odor during exercise. This makes clear that cabin climate is not a passive background condition. Human bodies, electronics, sunlight, shadow, and vehicle operations all add or subtract heat in ways that must be managed. In microgravity, warm air and cool air do not separate naturally in the familiar way they do on Earth, so ventilation and heat removal become even more important. The cabin must remain livable not only when the crew is sitting quietly, but also when they are working, eating, exercising, and sleeping inside a compact volume. Thermal control therefore belongs to the daily fabric of cabin life, quietly shaping comfort, alertness, and equipment reliability at the same time. Water is handled with the same controlled logic. NASA says Orion's crew module includes water tanks and a dispenser that provide drinking water and a simple way to rehydrate and warm food. While the newer Life in Orion fact sheet adds that the potable water dispenser supports meal preparation, drinks, and medical needs. That fact sheet also notes that the dispenser connects to 4 pressurized tanks in the service module through manual valves and quick disconnects. This arrangement shows that water in Orion is not just stored somewhere in the cabin as loose supplies. It is routed through a managed delivery system, one that turns stored water into something usable in a confined microgravity environment. Water must be drinkable, accessible, and easy to handle without free-floating spills. Even the act of preparing a meal therefore becomes part of the life support loop, because the cabin's habitability depends on controlled access to one of the most basic materials of life. Waste management completes the loop in a way that is easy to overlook but impossible to do without. NASA says Orion's waste management system, or lavatory, is designed for multi-week missions and privately accommodates both sexes in zero gravity. The Life in Orion fact sheet identifies it more specifically as the Universal Waste Management System, a compact toilet of about 5 cubic feet that uses airflow to manage both urine and solid waste in microgravity. NASA says solid waste is stored in odor-controlled canisters, while pre-treated urine is vented overboard daily. These details matter because a spacecraft cabin cannot remain livable if waste is treated as an afterthought. In a small sealed volume, hygiene, odor control, privacy, and reliable collection all become part of the same life support responsibility as oxygen and pressure. Waste handling in Orion is therefore not separate from habitability. It is one of the conditions that makes habitability real. NASA also highlights the role of fault tolerance in Orion's life support design, noting that deep space missions do not allow the quick return options available from the International Space Station. The crew systems reference states that Orion provides an ECLSS that is fault-tolerant and less complex than some earlier NASA human spacecraft, and it adds one especially revealing emergency capability. Orion's closed-loop life support system can maintain a positive pressure, breathable atmosphere, and thermal cooling for up to 144 hours to suited crew members in the event of a pressure vessel leak or contaminated cabin atmosphere. This means the ordinary cabin loop has a backup condition built into it. If the main inhabited volume becomes compromised, the spacecraft and suits together can sustain life for days rather than minutes. The calm routine of cabin life therefore rests on layers of protection beneath it, including the possibility of continuing survival, even when the normal cabin environment is temporarily lost. So this 12th layer of the mission remains entirely within Orion's life support loop. The spacecraft continuously manages pressure, oxygen, carbon dioxide, humidity, temperature, water, and waste through a set of systems designed for deep space efficiency and fault tolerance. It circulates and cleans the air, removes moisture and heat, dispenses stored potable water, isolates and stores waste, and watches the cabin environment for signs of danger. In this closed interior cycle, humans heading back toward the moon depend not on a single heroic machine, but on a steady invisible ecology of support, a manufactured atmosphere and daily material balance that must work hour after hour so that the small world inside Orion remains livable. By this point in the mission, Orion is no longer understood only as a spacecraft carrying people. It is also a workplace in which 4 astronauts perform distinct but overlapping duties. I'm continuing with section 13 and replacing the cut-off fragment with a complete section. I'm checking NASA's Artemis II operations notes so the crew tasks stay accurate and bounded to onboard work only. Section 13. By this point in the mission, Orion is no longer understood only as a spacecraft carrying people. It is also a workplace in which 4 astronauts perform distinct but overlapping duties as the vehicle is tested in real flight. NASA identifies Reed Wiseman as commander, Victor Glover as pilot, and Christina Koch and Jeremy Hansen as mission specialists. Those titles matter because Artemis II is not a passive ride around the moon. It is a crewed test flight in which the astronauts help judge how well Orion functions as a deep space spacecraft. NASA's press kit says the mission is designed to prove Orion's life support systems are ready to sustain crew on future missions and to allow the crew to practice operations essential to Artemis III and later flights. The human work inside the cabin is therefore part of the spacecraft's evaluation, not separate from it. The structure of that work begins very early. NASA's mission daily agenda says that after Orion reaches space and the interim cryogenic propulsion stage raises the spacecraft into a high Earth orbit, the crew has about 23 hours to conduct a thorough checkout of Orion's systems while still relatively close to Earth. This period sets the tone for crew operations across the mission. The astronauts do not wait until lunar distance to begin serious testing. They start almost immediately, using the first day in space to confirm that the spacecraft can support daily life and controlled work in the actual environment of flight. NASA says they test the potable water dispenser, the toilet, and the system that removes carbon dioxide from the air, and they rearrange Orion's interior into a living and working space for 4 floating people over the next 10 days. These are ordinary tasks in appearance, but they are foundational in meaning. The crew's job is to turn a launched spacecraft into a functioning habitat and command room. One of the clearest operational duties comes during the proximity operations demonstration. NASA states that after Orion separates from the upper stage, the crew uses that stage as a target for a manual piloting test. Mission controllers in Houston monitor as the astronauts transition Orion to manual mode and pilot its flight path and orientation around the target. NASA explains that this demonstration provides performance data and operational experience needed for future rendezvous, proximity operations, docking, and undocking in lunar orbit. In this sense, the crew is not only observing the spacecraft, they are actively flying it in a regime that future missions will depend on. Their manual work becomes a rehearsal for later flights, in which Orion must approach other vehicles safely and deliberately. The task also reveals the practical value of having a commander, a pilot, and mission specialists. The spacecraft is flown by a team, not by a single heroic operator. Manual operations are distributed, monitored, and integrated with ground support. After the proximity operations test, NASA says the crew turns control back to mission controllers and spends the remainder of the orbit verifying spacecraft performance. This relationship between crew and ground remains central throughout Artemis II. The astronauts are not independent in the sense of being cut off from Earth, yet they're not merely passengers receiving instructions. NASA's materials show an ongoing partnership. The crew performs checkouts, configures systems, executes procedures, troubleshoots, and records observations, while mission control monitors data, helps assess results, and refines the plan as needed. The operation style of Artemis II is therefore collaborative and procedural. Human judgment in the cabin is paired with continuous support and analysis from the ground. That is one reason the mission matters as a test flight. It validates not only hardware, but the joint pattern of onboard work and remote oversight that later deep space missions will require. The daily agenda also shows that different astronauts take the lead on different activities. On Flight Day 2, NASA says Wiseman and Glover begin by setting up and checking out Orion's flywheel exercise device, while Koch and Hansen exercise later in the day. The same day, NASA says Koch prepares Orion's systems for the trans-lunar injection burn, configuring the spacecraft for the main engine firing that sends the crew toward the Moon. On Flight Day 3, Hansen prepares for the first outbound trajectory correction burn. Koch later tests Orion's emergency communication system on the Deep Space Network. Wiseman and Glover check medical kit items including a thermometer, blood pressure monitor, stethoscope, and otoscope, while Glover, Koch, and Hansen demonstrate cardiopulmonary resuscitation procedures in space. These details show that the crew roles are flexible but real. The commander and pilot do not monopolize spacecraft work, and the mission specialists are not passive observers. Each astronaut becomes part of a rotating pattern of preparation, verification, procedure practice, and system evaluation. As the mission moves outward, operational work broadens from internal checkouts to observation and documentation. NASA says the crew rehearses the choreography for their scientific observation work before the lunar flyby, studies geographic targets, and later devotes much of Flight Day 6 to taking photographs and video of the Moon and recording observations in real time. During the flyby behind the Moon, communication with Earth is lost for roughly 30 to 50 minutes, depending on launch date. Yet the astronauts continue making visual records and spoken observations, so the material can later be matched to exact images. This work is important because it makes the crew not only operators of spacecraft systems, but trained witnesses. Their role is to look outward through Orion's windows, gather imagery, and translate a changing visual encounter into useful observational material for later analysis on the ground. NASA's agenda also shows that crew operations include repeated preparation for contingencies. The astronauts practice emergency communications, test their Orion crew survival system suits in space, and rehearse procedures that would matter if cabin conditions changed unexpectedly. On Flight Day 5, NASA says they test how quickly they can put the suits on and pressurize them, install their seats, and get into them while wearing the suits, and eat and drink through a port on the helmet. This kind of work is quiet but essential. Artemis II is a mission of validation, and validation requires proving not only that normal operations function, but that abnormal situations can be met with trained coordinated action. The crew therefore serves as both operators and evaluators of emergency readiness. So this 13th layer of the mission remains entirely within the astronaut's working role inside Orion. Wiseman serves as commander, Glover as pilot, and Koch and Hansen as mission specialists. But their real significance lies in the way they share the flight's operational burden. They configure systems, perform checkouts, fly Orion in manual mode during proximity operations, prepare engine burns, test communications, evaluate medical and survival equipment, rehearse emergency procedures, and document the moon during the flyby. In these duties, humans heading back toward the moon are not simply being carried through space. They are actively proving that a deep space spacecraft can be lived in, worked in, guided, and trusted by the people aboard it. Beyond low Earth orbit, the human body enters a condition that is familiar in principle from earlier missions and yet newly significant in practice. Artemis II carries its crew away from the region where human spaceflight has spent most of the past half-century, and that change matters because distance alters the physical setting in which the body must work. Inside Orion, the astronauts remain sheltered, supplied with air, water, and controlled temperature. But the body does not mistake the cabin for Earth. Weight is no longer felt in the usual way. Movement changes. Orientation changes. The relation between effort and posture changes. What had once depended on a floor, a ceiling, and the constant pull of gravity is replaced by floating, restraint, and careful use of limited interior space. NASA treats Artemis II as a chance to learn more about human health and performance under these conditions, because the crew is not only traveling through deep space, the crew is also becoming part of the scientific record of how deep space travel acts on the body and mind. Microgravity is the first reason for that attention. In orbit and on the translunar path, the astronauts live in continuous free fall, which creates the experience commonly described as weightlessness. The body adapts quickly in some ways and less comfortably in others. Fluids shift upward, changing the familiar distribution of blood and pressure in the body. Balance cues from the inner ear no longer match ordinary visual expectations. Movement through the cabin can become smooth and efficient after practice, but the first adjustment period can bring disorientation or discomfort. NASA's Human Research Framework for Artemis II explicitly includes the study of sleep, stress, cognition, teamwork, and other performance factors in deep space, reflecting the fact that bodily adaptation is never purely mechanical. The body and mind adjust together, and the mission environment tests both. Radiation adds a second layer of bodily reality. Low Earth orbit still benefits in part from Earth's magnetic shielding, but Orion travels into a more exposed region where the crew encounters the deeper space environment more directly. NASA's Artemis II daily agenda states that the astronauts will assess their ability to protect themselves from high radiation events such as solar flares, and will use Orion's supplies and equipment to build a shelter for cover if needed. NASA's Artemis II Science Overview also says that equipment aboard the mission will monitor radiation levels inside and outside Orion to characterize the deep space environment. This means radiation is not treated as a distant abstract hazard. It is an active operational concern built into the crew's lived routine. The body remains inside a shielded spacecraft, but the crew must understand that shielding as something to be evaluated, supplemented, and trusted under conditions farther from Earth than any human mission has reached in many decades. Sleep is another part of this bodily adjustment, and NASA is studying it closely. The agency's Archer investigation is designed to measure astronauts' well-being, activity, sleep patterns, and interactions during the Artemis campaign. NASA says participating crew members wear movement and sleep monitors, called actigraphy devices, before, during, and after the mission, so that researchers can study how sleep and activity patterns affect health and performance. Artemis II materials also show scheduled sleep periods within the mission timeline, including roughly 9-hour and 8.5-hour sleep blocks on different flight days. These facts reveal something important about the body in deep space. Rest is not left to chance or personal preference alone. It becomes part of flight design. A crewed lunar mission depends on cognitive clarity, emotional steadiness, and physical readiness, and those depend in turn on sleep that must be protected within a noisy, compact, unusual environment where sunrise and sunset no longer govern the body in the familiar terrestrial way. Exercise belongs to the same logic of preservation. NASA states that the Artemis II crew exercises on Orion using a flywheel, a cable-based device for aerobic and resistance workouts that can support rowing, squats, deadlifts, and other movements, with loading up to 400 pounds depending on crew effort. The daily mission timeline includes repeated exercise periods, showing that physical training is not optional recreation, but part of the mission's daily maintenance of the body. In microgravity, muscles and bones do not experience the same regular loading they do on Earth, and astronauts must work deliberately against that absence. Even on a relatively short mission such as Artemis II, NASA includes exercise because the body begins responding to reduced loading quickly. Exercise therefore becomes a way of reintroducing controlled strain into a setting where ordinary movement is no longer enough to preserve familiar physical patterns. Confinement changes bodily life in quieter ways. Orion's crew module is built for 4 astronauts on a mission lasting about 10 days, and that means every action happens within a tightly shared volume. NASA's descriptions of life inside Orion emphasize that the cabin must support eating, hygiene, exercise, work, and sleep in a compact environment. The body never forgets that the habitat is small. Every movement must account for another person, another workstation, another stowed object, another scheduled task. Privacy is limited. Personal space is reduced. Small routines therefore matter more than they do on Earth. The placement of food, the timing of rest, the order of cleanup, and the rhythm of work all become part of bodily stability. What the astronauts experience is not hardship in the dramatic sense, but constant closeness, a disciplined coexistence in which comfort depends on coordination as much as on equipment. NASA is also interested in how this environment affects teamwork, stress, and cognition. The Artemis II reference guide states that researchers will use the mission to explore how deep space travel affects sleep, stress, cognition, and teamwork, and NASA's human research pages similarly describe the study of well-being and behavioral performance during the mission. This reveals the body as something broader than muscles, bones, or exposure to radiation. In spaceflight, performance is embodied thought, attention, mood, reaction time, and social steadiness are all part of how a crew remains safe and effective. Deep space introduces isolation, confinement, and continuous responsibility, and NASA treats those as measurable influences on human performance, rather than as vague psychological background. The body in Artemis II is therefore both biological and operational. It is a physical organism, but also the medium through which judgment, timing, memory, and crew coordination are expressed. Medical readiness follows from that same view. NASA's daily agenda says the crew will check medical kit items such as a thermometer, blood pressure monitor, stethoscope, and otoscope, and will even demonstrate cardiopulmonary resuscitation procedures in space. Other mission activities include testing suits, emergency communications, and procedures related to abnormal cabin conditions. These details show that Artemis II treats the body not only as something to be protected during normal operations, but as something that must remain manageable when conditions depart from the ordinary. The crew studies the spacecraft, but the crew also studies itself, practicing the means by which health can be monitored, small problems detected, and larger emergencies faced within a vehicle far beyond rapid terrestrial help. In deep space, bodily vulnerability is not ignored. It is built into mission operations with calm precision, so this 14th layer of the mission remains entirely with the human body beyond low Earth orbit. Artemis II exposes its crew to microgravity, radiation concern, altered sleep rhythms, confined living, structured exercise, and the demands of sustained teamwork inside a small spacecraft. NASA is using the mission to gather data on well-being, activity, sleep, performance, and exposure, while the crew carries out practical routines that preserve strength, alertness, and health. In this setting, humans heading back toward the Moon experience deep space not as an abstract destination, but as a physical condition acting quietly on the body hour by hour, requiring constant adaptation so that exploration can remain calm, deliberate, and safe. Artemis II reaches its innermost meaning when the machinery, the trajectory, and the daily routines are understood not as ends in themselves, but as proofs. NASA repeatedly describes the mission as a test flight, and that description explains why the crew flies around the Moon without landing, why Orion's systems are checked so extensively, and why the mission is treated as a foundation rather than a culmination. Artemis II exists to confirm that the integrated deep space system works with human beings aboard. The mission is historic in its distance and symbolism, but its practical core is verification. Humans head back toward the Moon in order to learn, in flight, whether the spacecraft, rocket, teams, and procedures are ready for the harder missions that follow. NASA's mission pages state that Artemis II builds on the success of the uncrewed Artemis I mission and will demonstrate a broad range of capabilities needed on deep space missions. The press kit says the test flight will confirm the systems necessary to support astronauts in deep space exploration and help prepare a sustained presence on the Moon. This language reveals the mission's deepest logic. Artemis II is neither a repetition of Artemis I nor a premature attempt to do everything at once. Artemis I proves that the hardware can fly without crew. Later missions seek lunar surface operations. Artemis II is the human bridge between those two states. It asks whether the same architecture that has already flown uncrewed can now be trusted with 4 people inside it, not in simulation, not in a chamber, but in deep space. That is why NASA places such weight on life support. The launch announcement states that one of the mission's objectives is to demonstrate life support systems for the first time with crew aboard. The Artemis II reference guide says the flight will prove Orion's critical life support systems are ready to sustain astronauts on longer duration missions ahead. At the core of the mission, this is a simple human question turned into engineering. The central issue is whether the spacecraft can remain a livable world for its crew while moving far beyond low Earth orbit. Air, temperature, water, waste handling, cabin monitoring, and emergency capability are therefore not peripheral technical details. They are among the mission's central truths. A future lunar program cannot proceed on ambition alone. It needs a spacecraft that can sustain people reliably in the deep space environment, and Artemis II is where that claim is tested with real bodies and real time. NASA also identifies crew performance itself as part of what must be proven. The press kit says Artemis II will demonstrate the ability of systems and teams to sustain the flight crew in the flight environment and through their return to Earth. The phrase systems and teams is important. It shows that the mission is validating not only hardware, but also operations. Mission control, launch teams, recovery teams, communications networks, procedures, checklists, and crew coordination all belong to what Artemis II is designed to confirm. A spacecraft can be technically sophisticated and still be incomplete as an exploration system if the human and organizational parts do not function together under actual conditions. This mission therefore tests the full pattern of exploration, from the ground to the crew to the recovery forces waiting on Earth. Its core purpose is to turn a set of impressive components into a demonstrated human mission capability. The manual flying tasks fit into the same purpose. NASA's Orion operations material says Artemis II gives astronauts their first opportunity to ensure the spacecraft operates as designed with humans aboard, ahead of future Artemis missions to the moon surface. The proximity operations demonstration after separation from the upper stage is therefore more than a skills exercise. It provides data on how Orion handles, how its controls feel in real flight, how the crew interfaces with the spacecraft, and how operational techniques can be improved before later missions require more demanding rendezvous and docking work. A test flight, in this sense, does not merely ask whether the spacecraft survives. It examines how well it can be flown by the people who must depend on it. Artemis II turns the astronauts into evaluators of handling qualities, workload, and human-machine fit. This helps explain why the mission matters even without a landing. NASA frames Artemis II as a key step toward long-term return to the Moon and future missions to Mars. That framing is sound because exploration programs advance through validated capability, not through symbolic leaps alone. Before crews can descend to the lunar surface again, NASA must know that Orion can launch with crew, travel through deep space, sustain life, be manually operated when required, return at lunar speeds, and do all of this within a working system of teams and procedures. Artemis II is the place where those separate claims are bound together into one demonstration. Its achievement lies not in reaching a new surface, but in reducing uncertainty at the level where future missions become more credible. NASA's science description adds another layer to this inner purpose. It says Artemis II science operations will lay the foundation for safe and efficient human exploration of the Moon and Mars. The crew will work with scientists on Earth to facilitate investigations that inform future human spaceflight missions. This means the mission's core is not limited to engineering certification alone. Artemis II also begins gathering operational and scientific knowledge about how humans function, observe, and work in the cislunar environment. Radiation measurements, performance studies, sleep and stress data, and lunar observations all become part of a broader body of knowledge that later expeditions can use. The mission is therefore foundational in two senses at once. It tests the vehicle, and it also enlarges the understanding needed to use such a vehicle well. In the deepest view, then, Artemis II is a mission of earned confidence. NASA's descriptions emphasize readiness, confirmation, proving, and laying foundations. Those words point toward the same central idea. Deep space human flight cannot be assumed into maturity. It has to be demonstrated piece by piece until a living system of transportation, survival, control, and return has been shown to work with people aboard. Artemis II is where the showing happens for the current generation of NASA lunar hardware. The mission carries 4 astronauts around the Moon, but at its core it carries a challenge that only real flight can resolve. By the end of Artemis II, NASA seeks not abstract hope, but evidence. That is the innermost purpose of the journey and the reason the mission matters even before later landings begin. The mission then settles into its quiet final meaning. a spacecraft that begins on the Florida coast, rises on columns of fire, crosses the Earth-Moon distance, circles the far side of the Moon, and returns through Earth's atmosphere, leaves behind more than images and milestone language. It leaves a measured increase in trust. Artemis II does not claim that every challenge of lunar exploration is complete. It shows that a path is opening again, carefully and step by step, through systems that have now carried human beings away from Earth and safely back. Inside Orion, the crew lives for days within a small protected world, depending on air that is circulated, water that is dispensed, heat that is moved, and procedures that are repeated until they become calm routine. Outside, the spacecraft continues through silence, sunlight, darkness, and the long geometry of the cislunar path. Around all of it, teams on Earth remain present in voice, data, planning, and recovery. The mission is large in public meaning, but intimate in lived experience. It becomes a matter of 4 people, 1 spacecraft, and a sequence of systems doing exactly what they are meant to do. In that way, Artemis II restores something that has been absent for many years. Human beings once again travel beyond low Earth orbit with modern hardware, international partnership, and a deliberate view of what lasting exploration requires. The Moon remains outside the windows, ancient and quiet. Earth remains behind them, bright and familiar. Between those 2 worlds, the spacecraft carries its small cabin of breath, thought, work, and rest. When the journey ends, what remains is not only the fact that people have gone around the Moon again. What remains is the steady sense that deep space human flight has resumed its outward rhythm. The next missions are still ahead, but the distance has been crossed once more, and crossed with care.